In electronic course, you might remember, Larry, we were talking about circuits which had a feedback. And we were calling some circuit has negative feedback. And some had positive feedback. And we were talking about A, the gain of the circuits that we have over the feedback. Why we were calling it negative? Because if we were calculating the gain was always a positive number.
You feed the output to the negative input.
Yes, in other words, we will try to reduce if we have some kind of shooting. That's why we were calling it negative feedback. So if we are solving some numerical example and we come with some positive number, it doesn't mean that it is a positive feedback. If it is positive feedback, this is in general not good. Why? Because it means that if you put some distortion into your input, what will happen if you have positive feedback and you put a distortion into input, what will happen? Yeah, if it become bigger and bigger and bigger and bigger, it can cause some overshooting. But if you have a negative one, if you have a distortion in couple of iterations, maybe it will go to 0, right? Do you know an example of a positive feedback? With high probability you have heard and have practically seen it maybe 100,000 times.
Plus output.
No, in the real life. I give you a real life example.
I was thinking about the atomic bomb, but I haven't seen it.
No. Have you seen this? Hello. Ooh, it start to beep. This is an example of that one, because it starts. My voice started to go there and be amplified and be amplified and be amplified, so I start to have that beep voice. Now, of course, we have this directional microphone. You can just simply move it a little bit and it will be okay. Now, let's do an example on operational amplifier. And we have an integrator. So what we want to do, we want to find out what is the relation between input and output, right? What is the relation between input and output? What are the facts that we know? We know IT here is 0. We know that these two have the same voltage, right? Which is equal to 0, which is equal to 0. Why? Because this is grounded, so it means that this is also terms virtually grounded, right? Virtually grounded. Now, it's a very easy circuit in a sense that we know the current which pass into here will go also all through here. So we can calculate the relation between V out and V in. What is the current? What is the formula for the current? Let's call it IT. IT is equal to V positive minus V negative, which is 0, divided by R1, right? Now, we can write the same thing. We can write the same thing for the upper part. We can write the same thing for the upper part. Let's use the KVL, and we know that VOT is equal to this voltage plus this voltage is IT R2 plus VC, the voltage of the capacitor. So how many unknowns do I have? We know VO, we want to find the VO, we know VI, but I have to somehow turn this VC either in terms of VO or in terms of VI. I know that IT, I can write it, I can replace it as terms of VI, right? IT, I can write it as terms of VI. What about the VC? What can I do regarding to VC? Come on, we all know what is the equation for VC, don't we? What was the name of this circuitry? I said it is called? This op-amp is making it's an integrator. So it means that if it isn't an integrator, we should have an integration somewhere. But where is the integral? What is the relation between VC and integral?
We can write integral.
Yes, VC is the integral of the current. So what I want to do is this actually. I am replacing IT with VIT, R1. So I write V0T is equal to VIT divided by R1 multiplied by R2 plus VCT. And I find the derivative of both sides. So what happens is I have the V0 dt plus is equal to R2 over R1 d VIT dt plus and the VCT dt, right? dVC over dt, what is this? It is? You mean IT over... Well, IC is IT, the same current is passing through. So it's IT divided by C. So VOT dot is equal to R2 over R1 VI dot T dt plus this is IT over C. But what is IT? It's VIT over R1. VOT dot is equal to R2 over R1 VIT dot plus 1 over C R1 VIT. I know the thing that I will write here, you already know it, but in any case, for safety, we write it down again. For resistor, Vt is equal to RIT. For capacitor, Vt is going down, and IT, and capacitor is C. IT is C dVt over dt. For inductor, with the inductance of L, we have Vt is equal to L dit dt. Now, in all the examples that we solved, we had one thing in common. We solved for translational mechanical, rotational mechanical, and RLC circuits. Well, we had one thing in common. What was that? They were all linear systems. So what we want to talk is, what happens if it is not linear? We want to do the linearization. And another words, systems. So we want to learn linear systems, linear control, but we know that we don't have linear system most of the time. So the question is that how we can figure out if the system is linear or not, and how we can approximate it with a linear system. As an example, let's start by talking about this. Consider a rotational pendulum, which is which we have the angle theta, which is changing, which is causing the momentum or of tau. Then we can write down momentum of inertia, which was J, is actually mL squared. M is the mass of the ball which we have there. So the summation of M, which is equal to J alpha, which is the angular acceleration, theta double dot. So it will be the momentum minus the mgl sine theta. Sine theta. So then we can write the system as theta t plus mgl over j sine theta is equal to tau t divided by j. So this is the set of equation that we have. Now, what happens here is the variable that we try to calculate is theta t, the angle as a function of time, and the input is the moment that we are applying, right? But one thing that we can understand easily is sine function is not a linear function, right? So this means that this differential equation that we have is actually nonlinear, which makes all the examples that Morteza solved last week cannot be used. So what we do is this. We know if theta is small enough, then we have sine theta is approximately equal to theta itself. And what is the meaning of small enough, Abdulaziz? It means that if the angle is less than 6 degrees, if you write it in radian, you will see that the sine theta and the theta is almost the same with a good approximation. Now, in that case, what we have is easy to solve, or at least easy to understand differential equation. This is called linearization. So this is an overview of what we want to do. Okay, for sine, it's easy. We knew it from mathematics, from calculus, that if the theta is small, sine theta and theta are the same. However, what will happen if it is not sine, it's another function which is not linear function? How? We can approximate it by using mathematics. And actually we can write this one. We can convert any differential equation into a first order vector differential equation, which means that x vector dot is the function of x and an input u this is a vector and u is the input. So we can do it if and only if, so there is an if and only if for this statement. We write it IFF, which means if and only if the system is linear. Because this is a very good and important property, we want the system to be linear, or we want to approximate with a linear system. This will be of the form AX plus BU, where A and B's are constant matrices. Okay? So that's why we need to have a linear system, because we want to use this ability. Now, we will see in the next lecture that in order to do that, we are using a very, very good mathematical tool, which is called Taylor series. Do you remember Taylor series? Taylor series was telling us that I don't care if you have a sine or exponential function or logarithmic function. We can write it down as terms and series of some linear functions. And we will see how we can do that. And then we will see that where we can actually truncate We understand that even if we use this approximation, there is an error. We accept that error, but that error is very small. In other words, you're sitting in your car, you don't mind if you go in Tallinn, you have a very, very slight vibration. Right? Very slight vibration is okay. Maybe even our body cannot feel it. So it means that what the calculation, or not only the calculation, because this approximation means that the way that you will build your system will be cheaper even. So you will spend, let's say, 20,000 euro less on a car, but you have maybe a very, very minor vibration which even the body might not feel. Do you have any question? If not, we will talk about this linearization. Afterwards, we will go back to the dynamic response.